I'm tackling a problem about how to fine-tune a lasso regression model. Lasso, short for least absolute shrinkage and selection operator, is a type of regression that shrinks coefficients to zero and is particularly helpful with highly correlated data. We'll be adjusting the settings, hyperparameters, to make it work even better. My LassoCV model, LassoCV, uses cross-validation to automatically choose the best penalty strength. Alpha isn't performing as well as it should. I suspect it's because the penalty strength, alpha, setting is not optimized. This means the model is not effectively managing the trade-off between fitting the training data and generalizing well to new data. I'm investigating several things I can do to improve the model. The goal is to select all the actions that could help solve the issue. I can increase the number of folds in cross-validation. Think of folds as splitting my data into multiple subsets. We train the model on most of the data and test it on the remaining part. More folds mean a more accurate assessment of performance, which will improve the reliability of alpha selection. I can decrease EPS, which controls how precisely the algorithm solves for the best coefficients. A smaller EPS might lead to a more accurate solution, but it's not guaranteed and could greatly increase computation time without significantly improving model accuracy. I can increase the number of alpha values tested. More values will allow for a finer search for the best penalty strength, alpha, potentially improving the model if the truly optimal alpha value was missed in the original search. I could consider using a different technique, like ridge regression. Ridge regression is another approach to handle correlated data, but it works differently than lasso, and switching is not guaranteed to be an improvement. It's an alternative and not a direct improvement to my current approach. I need to choose all options that will likely improve the model's performance given the current situation. I think increasing the number of folds in cross-validation, the _CV parameter, will improve the model's performance. More folds give me a more reliable estimate of the best regularization strength, alpha, reducing the risk of overfitting or underfitting. Similarly, increasing the number of alpha values tested, n_alphas, allows for a more thorough search, potentially finding a better alpha that I might have missed otherwise. It's like searching for gold. The more places you look, the better your chances of finding it. I don't expect decreasing the convergence tolerance, EPS, parameter to significantly improve the model. While stricter convergence can sometimes improve accuracy, the impact is usually less important than finding the right regularization strength. It's like tweaking a tiny detail while the main issue remains unsolved. It might increase computation time without a corresponding improvement in prediction accuracy. I believe that increasing the number of alpha values I test, n_alphas, will also lead to improved performance. A finer search helps me discover a better alpha which could be hidden between the initial values. Think of it like having a higher resolution image. You see more detail. I'll get a more precise alpha value. I'm tuning the hyperparameters in lasso regression, a technique to find the best fit line while preventing overfitting. Think of it like finding the perfect balance between simplicity and accuracy. Lasso uses a penalty to shrink some coefficients to zero, making the model simpler. We're trying to select the best penalty strength, or alpha, using cross-validation. My lasso regression model isn't performing as well as it should. I suspect the problem lies in how I've chosen the alpha parameter, which controls the penalty. It might be too strong or too weak. I'm dealing with a dataset where some variables are highly correlated, which is known as multicollinearity. This can make things tricky. To improve my model, I should increase the number of folds in cross-validation, improving reliability, and increase the number of alpha values tested, allowing a finer search for the optimal value. Both actions directly impact the selection of the optimal alpha value, which is central to improving performance with Lasso. I'll explain what LassoCV is and why its hyperparameters are important. LassoCV is a powerful technique in machine learning that performs lasso regression, a type of regression that shrinks coefficients towards zero, with built-in cross-validation. Cross-validation helps us choose the best value for the regularization parameter, alpha, without overfitting to our training data. Choosing the right hyperparameters, like the number of folds in cross-validation or the number of alpha values to test, is crucial to obtaining accurate and reliable results. It's like carefully adjusting the dials on a complex machine to get the best performance. I'm facing a problem where my lasso regression model isn't performing as well as I'd like. Because I suspect the main issue is the alpha parameter, I'm exploring ways to improve it. It's like a car that's not running smoothly. I need to find the right tune-up. I need to figure out which adjustments will improve the model's accuracy given the data has high multicollinearity. Many features are strongly correlated. This is a common problem in lasso regression, and careful hyperparameter tuning can help overcome it. Increasing the number of folds in cross-validation means I'll divide my data into more parts and train my model on more combinations of those parts. This will result in a more robust estimate of the best alpha parameter. Think of it like getting more opinions before making a decision. More opinions usually lead to a better decision. Decreasing epsilon, (eps), makes the algorithm more precise by setting a stricter convergence criterion. While it might yield marginally better results, it's not guaranteed to significantly improve the model and might increase computation time unnecessarily. This is like making very small adjustments. It may or may not be needed. Increasing the number of alphas, (n_alphas), means I'll test many more values for alpha during the cross-validation process. A broader search might reveal a better alpha parameter that wasn't found initially. This improves the chances of finding a better alpha. It's like searching a field with a finer-toothed comb. This is an alternative approach altogether. While ridge regression is also a regularization method, it handles multicollinearity differently and might be a better choice in certain cases, but doesn't directly address tuning LassoCV's hyperparameters. After analyzing all options, I've found that increasing the number of folds and increasing the number of alphas are the best approaches to improve the model's performance. They directly address the potential for poorly tuned alpha, the likely cause of the poor performance. I'm seeing that your lasso regression isn't performing as well as expected. This is a common problem, especially when you have variables that are highly correlated with each other. We need to improve its performance. Let's find out why. To choose the best regularization strength, alpha, LassoCV uses cross-validation. Increasing the number of folds makes this choice more reliable. Think of it like this: instead of splitting your data into just two parts, training and testing, you're splitting it into many more. The more folds, the more accurate you'll be at determining the best alpha. This should improve your model's performance. LassoCV tests different values of alpha to find the best one. Increasing (n_alphas) means I'll test many more alphas. This gives me a better chance of finding the optimal alpha, which might be hiding between those initially tested. A finer search means a potentially better model. (eps) controls how precisely the algorithm finds the best solution. Making it smaller means I'll get a more precise answer, but it might also take much longer to compute and might not significantly improve results. It's often less impactful than correctly tuning alpha. Ridge regression is another regularization technique, an alternative to lasso. It handles correlated variables differently. Switching to ridge regression isn't necessarily better, it's just a different approach. It's not a direct improvement for this particular LassoCV problem. These options address possible causes of poor performance of your lasso regression. I'm going to carefully evaluate each one. This problem focuses on optimizing the hyperparameters in your lasso regression model to achieve better results. I'm going to optimize the hyperparameters to improve the performance. This problem focuses on how to fine-tune the hyperparameters of lasso regression, a technique used to simplify complex models while minimizing prediction errors. We'll explore how tweaking different settings can improve the model's accuracy and efficiency. It's all about finding that perfect balance. The challenge here is that a lasso regression model isn't performing as well as expected. The suspect? Poorly tuned hyperparameters. I want to adjust these settings to potentially solve the issue. Let's get to work. Several options exist to improve lasso regression performance. I'll assess each and determine the best approach. Let's review our options. To improve lasso regression's accuracy, I'll increase the number of folds used in cross-validation. Think of folds as different subsets of the data I use to train and test the model. More folds provide a more robust evaluation of performance and better hyperparameter selection. More folds mean a more reliable result. The n_alpha's parameter controls how many different values of the regularization strength, alpha, the model tries. By increasing n_alpha's I'll get a more refined search. This will help the model choose the best alpha for the data. A wider search for the optimal alpha is a good idea. The _eps parameter determines the tolerance for the algorithm that solves the lasso regression problem. Decreasing _eps makes the algorithm more precise but might not significantly improve the final model's accuracy and could take longer to compute. This is often a minor adjustment and might not help as much as the other options. Instead of lasso, I could try a different method, such as ridge regression. It's a different regularization technique, and its suitability depends on the data characteristics. While this is a valid alternative, it's not directly addressing the identified tuning problem with the current model. I found the best approach is to increase the number of folds and increase the number of alphas. This approach tackles the root cause directly, improving the alpha selection process. I'm confident these adjustments will yield a better performing model. We're tuning the LassoCV model, which uses lasso regression and built-in cross-validation to automatically find the best regularization strength, alpha. It's like finding the sweet spot for balancing model complexity and accuracy. The LassoCV model isn't performing as well as we'd like because of potential issues with alpha tuning, the strength of regularization. We're trying to solve it by adjusting the parameters of the model. I'll explore several ways to potentially improve the LassoCV model's performance. We're looking at solutions which could address problems related to hyperparameter tuning and multicollinearity. I'd increase the number of folds in cross-validation. More folds give me a more reliable estimate of the best alpha, reducing the chance of overfitting or underfitting. This improves the model's robustness. Think of it like getting more opinions before making a decision. More data points improve accuracy. I'll try increasing the number of alpha values tested. A wider range increases the chances of finding the optimal alpha, leading to a better fit for the data. It's like searching more thoroughly for the best value. A finer search grid increases the possibility of finding the perfect spot. I could decrease EPS, which controls the convergence of the algorithm. A smaller EPS means greater accuracy, but potentially more computation time. While potentially helpful, its impact is often less significant than finding the optimal alpha, so I'd focus on other parameters first. I could switch to ridge regression, a different regularization method. However, this isn't necessarily an improvement, it's a change of approach, not a refinement of my current LassoCV approach. The best options are A and C. Increasing the number of cross-validation folds and the range of alpha values improves model reliability and the chance of finding the optimal regularization strength. These are the most direct ways to address the suboptimal alpha selection.